fundamental theorem of calculus, also we call it the FTC. So the fundamental theorem of calculus says that if our function's continuous, then if I integrate from a to b of f of x dx, I get big F of b minus big F of a, and the relationship between little f and big F is that f prime, big F prime, is equal to little f. So in general, that's what the fundamental theorem of calculus says. There are a couple of different ways that those problems show up, but almost always the way that fundamental theorem of calculus problems show up is something along the lines of taking the derivative of an integral. So if a problem's asking you to apply the fundamental theorem of calculus, chances are there's something in the problem that you can take the derivative of. Sometimes it's going to be very explicit. So maybe I'm going to tell you that I want you to take the derivative of this integral. Now, right here, if I'm taking a derivative with respect to x, that automatically tells me that I'm expecting to see x's here in the limit. So some kind of function of x, or it could just be a constant. But I'm going to go ahead and put some values in here. So let's say this is the square root of x, and this is x cubed. Now, another thing to note, in terms of this integral, I am expecting to have a different letter here that is not x, that involves the integrand and the d something. So for example, I might have something, let's say, sine of t squared dt. Now, this fundamental theorem of calculus tells me that just for the integral part, so if I just look at this piece of it, fundamental theorem of calculus says there is some big F function out there, and what we should do is plug in the top minus plugging in the bottom. So I'd have something that looked like F of x cubed minus big F of the square root of x. Now that's just the integral part. With this problem, we're taking the derivative of that. So now applying the chain rule, what happens over here, I'm taking the derivative of big F, so I would get big F prime of x cubed times, chain rule says I should multiply by the derivative of x cubed, or 3x squared, minus F, big F prime of the square root of x, times, chain rule says I should multiply by the square root of x, or 1 over 2 root x. That's applying this first part of the fundamental theorem of calculus. Well, we're not done yet, because this second part of the fundamental theorem of calculus tells us what big F prime is. So that means my big F prime should match with whatever the function was we were trying to integrate. So my final step here would be to replace that big F prime of x cubed by plugging in x cubed to the function inside of the integral. So I'd end up here with sine of x cubed squared times 3x squared minus f prime, so sine of this function, square root of x squared, times that chain rule piece, 1 over 2 root x. So that's one example of applying the fundamental theorem of calculus very directly. There are a couple of ways where this fundamental theorem of calculus problem could sort of be hidden inside of something. We could actually hide this inside of a differential equation. We could hide this inside of a limit that required using L'Hopital's rule. My guess is, from looking at the practice problems, both from Diddel's midterm and then also just knowing what he has put on midterms in the past, I think if you get a fundamental theorem of calculus problem, it's going to be fairly straightforward in the sense of we're going to know that we need to take the derivative of an integral. Methods for integrating. So we've got a whole bunch of methods for integrating, but they kind of fall under a couple of categories for me. So if the problem is just algebra, meaning I've got numbers times x's to powers, right? Something kind of in that realm. Things that we have up our sleeve. Well, we've always got the possibility of a u substitution, where the derivative of one part of the problem is equal to another part of the problem. If we have fractions, then we might have to think about long division. And long division is going to happen when the power in the numerator is greater than or equal to the power in the denominator. If our power in the numerator is not greater than or equal to the denominator, we might be thinking about partial fractions. If the denominators factor. We also might see problems that involve trig. So if I'm looking at integration problems that involve trig, I am still thinking about u subs. And another thing that comes up a lot of times in trig is actually needing to make some sort of trig identity substitution. Common ones that might show up in terms of being useful for integrals, knowing that tangent squared x plus 1 is equal to secant squared x. That's a common one. The other one that shows up sometimes, cosine squared x is equal to 1/2 of 1 plus cosine 2x. And sine squared x is equal to 1/2 of 1 minus sine of 2x. These are the three most common trig identities that you might have to use in order to get through an integration problem. Now, I generally put these into one of three categories: algebra, trig, or what I'm going to call a mixture problem. And I'll just say a mixture of stuff. Anytime that you have e to the x or ln, I'm putting that into the category of a mixture of stuff. When we have a mixture, I'm still going to start by thinking about a u substitution. But if there isn't a u substitution, and we're in this category, I am almost always going to have to switch to integration by parts. And our formula for integration by parts is that we start with something of the form u dv, and we rewrite that integral to be uv minus the integral of v du. So we swap out one integral for another. In terms of integration by parts, there is the possibility that that integration by parts cycles back on itself. And when it does that, we end up having to take a term, move it to the other side. And we've certainly done some examples of that this quarter. So one way to identify that it's an improper integral problem is actually the way the question is asked. So if I ask a question that looks like evaluate or show that it diverges, that phrase diverges, that's already a clue that this should be an improper integral. Now, we've talked about this quarter two ways that an improper integral can show up. One way is that we actually have an infinite limit. So either my upper bound, lower bound, or both could be infinite. So I might have something that looked like negative infinity to a number, or I might have something that looked like a number to positive infinity, or I might have something that looked like negative infinity to positive infinity. In general, with our indefinite or with our improper integrals, the first thing that we want to do is to replace wherever the infinity is showing up with a letter, and then take the limit as that letter approaches infinity. So in this case, I would switch that around to look like the limit as a approaches negative infinity, and then I'd go from a to 3. Here, I'd switch this to be the limit as, and the choice of letter doesn't matter, b approaches infinity, 5 to b. And in this case, if both of our limits of integration are a problem, then we actually have to choose a value in between and break this apart. Usually we choose 0. You don't have to choose 0. That's just kind of the most standard thing to choose. So in this case, I might break this apart to say the limit as a approaches negative infinity and go from a to 0. And then we would be adding that to the limit as b approaches infinity and going from 0 to b. And for each of those, we would still be integrating f dx. So. The other type of improper integrals that we talked about this quarter are ones where the infinity is actually in disguise. This second type is not in our textbook, but we talked about it in co-class, and Didel definitely talked about it in lecture. So the other type of improper integral we can have is one where the function itself has a vertical asymptote, or it's undefined somewhere in the interval. So maybe this is going to look something like, let's say that I have the integral from 1 to 10. So neither of those limits are infinite, so I wouldn't immediately be thinking about it as an improper integral. But if I then came in and did 1 divided by the square root of x, no, let's not do a square root. Let's say 1 over x minus 3 squared dx. So here, neither of the limits are infinite, but this function is undefined when x equals 3. So even though this didn't look like an improper integral, we still have to break it up at that x equals 3 point. So I'd have to think about this as being the integral from 1 to 3 plus the integral from 3 to 10. And then to make it proper, we'd come in and replace that 3. Come in and replace that 3 with a letter. So I'd be looking at the limit as a approaches 3. And I'd still have that same function, the 1 over x minus 3 squared dx. And here I'm going to replace that 3 with another letter. So I've got the limit as b approaches 3, again, keeping that same function. For both of these, if I want to get all of my points on the problem, there is a subtlety that we want to keep in mind. So originally, this integral went from 1 to 10. And we broke this apart at 3. So when I'm looking at the portion from 1 to 3, all of those values are on the left-hand side of 3. So I want to come into this limit and put a minus sign. When I look at the portion from 3 to 10, all of those values are on the right-hand side of 3. So I want to come in and put a plus right there. So those are the two types of improper integrals that we might see. To answer this question in terms of evaluate or show that it diverges, remember that when we finish off that limit, if we get positive infinity, negative infinity, or that it's undefined, all of those are going to tell me that the integral diverges. But if we get any number at all, 0, negative 17, 4/3, if I get any number at all when we're done, then I've evaluated it. It does not diverge. We could also say that it converges. One thing to note when we are, so there's a question in there about if one part of the integral diverges, then the entire thing diverges, correct. So if you've done one part of it and you already got an answer of infinity or negative infinity, then you can right there just stop and say, it diverges. Yeah. In terms of evaluating those limits, common limits that come up in these kinds of problems, I don't even need to erase it really. So thinking back to 17a and just quick limit review, if when you plug in the number, you get a number divided by 0, that's going to be an infinite limit. We know that that's going to diverge. If I get 0 over 0, that would tell me to do more work. And usually the more work is to think about applying L'Hopital's rule. If you get infinity over infinity, that also says we need to go do more work. We're going to be thinking about L'Hopital's. Other common limits that show up here, if I have e to the 0, that's equal to 1. If I have e to the positive infinity, that is headed to positive infinity. And if I have e to the negative infinity, that is headed to 0. The one other limit that instructors like to make show up in here involves arctan. So just as a refresher, tan inverse of infinity is asking us what's the angle where tangent is approaching infinity. And that angle is pi over 2. Kind of as a general rule, we're going to get that area by integrating the top function minus the bottom function. If we are talking about a dx, or if for some reason we have an area where the functions are defined as functions of y, then our area will end up being a right-hand side minus a left-hand side times dy. Usually if we're doing an area problem, one of the things we might have to find is points of intersection. And we're going to set the function, we're going to set our two functions equal to each other to find those points of intersection. So let's say that I asked us to find the area of the region bounded by, I'm going to keep our lives simple today, so let's make this y equals x to the 4th and y equals 2x cubed minus x squared. Okay, so if I had to find the area, I need to know which function is on top and which function is on the bottom. And to get those limits of integration, I also need to know the intersection points. So if I'm not sure what those graphs look like, I'm going to start by finding the intersection points. And that's actually going to help me figure out who's on top and who's on the bottom. So to find the intersection points, I'm going to set these two equal to each other. So I'm looking at x to the 4th is equal to 2x cubed minus x squared. I'm going to put all of that onto one side so that I've got a 0. So x to the 4th minus 2x cubed minus x squared is equal to 0. Then I try to make this work out in my head. Let's see how it happens. So I can factor in x squared out of each term. And then I'm left with x squared minus 2x. Oh, wait, that should be a. Okay, that's why I don't touch the board with my fingers. When I moved that over, that should have been a plus x squared. Sorry about that. So when I pull out an x squared, I'll have a plus 1. Now I think I managed to make something that factors. So I'm looking at x squared. And then this, I think, factors as x minus 1 whole thing squared. So I know that these two graphs intersect at two x values, at 0 and at 1. So if I think about 0 and 1, I just need to know, for some number in between here, which of these is bigger. So if I were to choose a number like x equals 0.5, then 0.5 to the fourth, sorry for making fractions, but 0.5 to the fourth should be 1/16. Actually, okay, what I'm doing will work, but I'm going to be lazier than that. What I did in here is I took x to the fourth and I subtracted the other function. So I'm going to call these y1 and y2. So this right here is y1 minus y2. If I plug in 0.5 here, I've got a positive thing because it's squared times another positive thing because it's squared. So if y1 minus y2 is positive, then y1 had to be bigger. So I know that in this region, the function on top had to be x to the fourth, and the function on the bottom had to be 2x cubed minus x squared. So not even knowing what the function looks like, I can still write what the integral is for the area. I would be looking at 0 to 1 of our top function minus the bottom function. And Adele did say on Wednesday that the area problem would just be a set up. So we have set up the area. It's going to look like our cross-sectional area times our thickness, which is either a dx or a dy. So our cross-sectional area, I'm just going to write that as times dx. So if we're talking about a volume of revolution and I'm spinning something, then that cross-sectional area is a circle. So if we have a volume of revolution, that cross-sectional area becomes pi r squared. Now, we have some subtleties here. So this dx implies that we revolved around something parallel to the x-axis. So that might be a value, that might be the x-axis, or it might be y equals -5, or it might be y equals 17, but it's something that is parallel to the x-axis. If what I'm revolving around isn't actually touching the axis, so for example, if I had some shape out here and I revolve it around the x-axis, well, we're not going to get a disc with a little bit of thickness, because if I take a cross section here and I spin around the axis, it's kind of hollowed out. We end up with something that kind of has this hollowed out core, which means that when we do this, we'll end up with a volume that's like a big volume minus a little volume, or a pi big r squared dx minus a pi little r squared dx, where that radius is measured from the axis of rotation to our functions, respectively. So in this case, for what I drew in, my little r would go from the axis of rotation to that lower function, and my big R would go from the axis of rotation to the upper function. That's all I'm going to say about volumes of revolution. The other kind of volume that we talked about this quarter, sometimes one of the hints that we'll see to know that it's the other kind of volume is you might see cross sections. So you might see the phrase cross sections show up in the problem, and typically, or it's going to say something like slices, And then usually it will say perpendicular to. So slices, or cross sections or slices perpendicular to, and then it might say x or y, and that's going to determine whether your integral should be written as dx or dy. And when you're talking about cross sections, the other way to know that it's one of these cross section problems is there will be some sort of geometric shape listed. So it'll tell us that the cross sections or the slices perpendicular to are squares, equilateral triangles, rectangles, and then give you a height. So rectangles with height, fill in a number, circles or semicircles. Those are the only shapes that I personally have seen show up in problems, either for Dedel or honestly any other calculus instructor. In terms of the textbook problems, some of these cross-section problems were actually having you use numerical methods to solve. So they were telling you what the area of the cross-section was, and then you just had to multiply by the thickness and add those up. So do volumes of revolution always include pi r squared? Yes, because the cross-section for a volume of revolution is always a circle. But your cross-sections might be circles, or they might be squares, equilateral triangles, rectangles with a particular height, or semicircles. So volumes of revolution, we're always looking at pi r squared, or potentially having to subtract like a big volume from a little volume, but it's still a pi r squared that's showing up there. But cross-sectional or slices perpendicular to an axis, then you're probably looking for one of these other shapes. To classify a differential equation, and I've been talking about this, or I keep mentioning it, but in terms of differential equations that we're going to solve, there are only two types of differential equations that we're going to solve, and that's if they're separable or first order linear. So if you're asked to solve it, it must be separable or first order linear. But within the category of separable, the textbook makes two distinctions. So for separable, or rather both of these are types of separable differential equations. There are other types of separable differential equations, but in this category, we have pure time differentials and we have autonomous. I think that's how you spell autonomous. So the distinction between a pure time and an autonomous differential equation comes down to what variables are involved in the problem. So if I were to tell you that the differential equation was written as dn dt, if what is on this side includes only n and no t's, oh, that looks like not. If it includes only n, not t, there we go. If it includes only n and not t, then this is autonomous. If this side includes only t and not n, then we would call it a pure time. But even if I change the variables up, we still call this autonomous and pure time. So for example, if I came over here and I made this dy dr, well now, because y is in the numerator, if this included only y and not r, then we would call it autonomous. And if it included only r and not y, we would call it pure time. So we call it pure time even if the variable isn't t, if the only variable involved is whatever's in the denominator for our differential piece. There are other kinds of separable differential equations. So if it's not pure time or autonomous, it might still be separable if this can be written, and I'm just going to make it a dy dx for a second. If I can write this as something with only x times something with only y. And again, this applies regardless of what the variables are. So if this had actually been dk dt, then I would need to be able to write this as only t times something with only k. So any of these forms we would call separable, but these two have particular names, autonomous and pure time. Now in terms of first order linear differential equations, that is anything that can be written in the very particular form of y prime plus something times y plus something, equals something. Where this, and in general, I'm going to say these have only x. Again, we can swap around the variables here, and I could make this x prime plus something x equals something, and maybe these have only t. Then we can solve it by separating and integrating the result, but we can also talk about the nature of solutions to an autonomous equation without actually doing any integration at all. So if I had an autonomous equation, maybe something like dn dt is equal to n minus 5 times 1 minus n over 10. If I have an autonomous differential equation, and one of the particular biological models that we looked at was logistic growth, and so logistic growth does represent an autonomous differential equation. So if I have an autonomous differential equation, one thing that we might be asked to find are equilibria. So equilibria happen when our derivative is equal to 0. We can also think about that like thinking forward ahead to section 8.8 or back to 17a when we were talking about recursion relations. This idea that the derivative is 0 indicates that something isn't changing. So when we're at equilibrium, our population distribution is not changing. Or in this case, when I'm at equilibrium, my overall population value is not changing. So I'm going to find our equilibria here. And so in this case, I've got n equals 5 or n equals 10. And we can find those equilibria and classify stability. Well, to classify the stability, we have two options. Option 1, we can graph it. And option 2, we can use the analytic, or sometimes referred to as the eigenvalue approach. Just as an aside for a second, there's a reason that this is called the eigenvalue approach, but we're really not going to see the connection between what we're doing with eigenvalues and solving these autonomous equations until 17c. So just hold on tight for tying those things back together. For now, just know that it's another name for that analytic approach. For the analytic approach, what we do is we call our differential some function. So I'm going to call this f of n is equal to dn dt. Notice we're not saying that it's a function of time, it's a function of n because this was autonomous. Once we write it this way, then we're taking the derivative of this function and evaluating it at our equilibrium values. If it's less than 0, then we say that it's stable. And if at our equilibrium value, f prime is greater than 0, then we say that is unstable. To use our graphical approach, we're going to take this, we're going to want to graph this where our axes are n and dn dt. So when we sketch this out, this is some kind of a parabola, and it should be concave down, because when I distribute this out, my n squared term will end up being negative. So we've got equilibria at 5 and at 10, and we know that it's concave down. So something like that for our parabola here. When we use the graphical approach, what's important is wherever this curve is above the axis, I know that represents dn dt being positive. And if dn dt is positive, n is increasing. So everywhere where the curve is above the axis, I should be moving towards bigger n values. In contrast, everywhere that we're below the axis, that represents dn dt being negative. And if dn dt is negative, n is decreasing, and I should be moving towards smaller n values. I like the graphical approach because for me, it's, well, one, I'm good at graphing, so that helps. But the other thing is, I can see that all of the population is moving towards a value of 10, or all the population is moving away from a value of 5. So that idea of stable, unstable just makes more sense to me graphically, why they would give it those names. All this, my f of n, then f prime, I'm going to use a product rule. Derivative of that first piece is 1, so I'll have 1 minus n over 10, plus, leave the n minus 5 alone, and the derivative of this would be negative 1/10. So if I look at f prime of 5, plugging that in everywhere, that's 1 minus a half plus, oh, well, 0. So 1 minus a half is positive. So that is greater than 0, which is going to tell me that it's unstable. If I repeat this and plug in the 10, plug in 10, when I plug in 10, that'll be 1 minus 1, so that part will be 0 now. And over here, 10 minus 5, so that's 5 times negative 1/10. So yeah, that's less than 0, so we draw the same conclusion. 10 is a stable equilibrium, whereas 5 is an unstable equilibrium. Y prime is equal to x minus y squared over x. If I had to classify this, well, it's not first order linear. It is first order, but that y squared term tells me that it's not linear. If this were going to be separable, I'd have to be able to write this side as something with x's times something with y's. The problem here is that if I tried to factor out one of those x pieces, I couldn't get the other one because this one's in the denominator and that one's in the numerator. So I can't write this as something with x's times something with y's. So in the context of 17b, I can't solve it. It's not separable and it's not first order linear. But if I told you that y of 1 was equal to 2, then I could ask you to approximate y of 1.2. Sure. And for Euler's method, there are a couple of things that we have to know. I have to know the starting point. I have to know the differential equation. But I also have to know something about the time step, or h, or delta x. to know something about the time step. So in this case, I know that I'm standing at x equals 1 and I need to get to x equals 1.2, but I haven't given us enough information to know how to get there. So I could give you that additional information in a couple of ways. I could say, using 2 iterations, or I could just tell you that the time step of h, or delta x, was equal to 0.1. And either of those 2 statements would be enough. So if I say using 2 iterations, that means I have to get from 1 to 1.2 in 2 steps. So that's a distance of 0.2. And if I do that in 2 steps, then each step would be a distance of 0.1. And we have a formula for Euler's method. And that formula is actually coming out of our equation for linear approximation. So to get my next y value, I'm going to start at the y value I'm currently on. And then I'm going to move in the direction of my derivative. And that's my derivative evaluated at the point I'm currently on. So I'm going to call that x sub n, y sub n. So I've got our derivative evaluated at the point I'm at times our delta x, or h. So just to go through the motions on this problem, for me, it's easiest to kind of set up a table. But if that doesn't work for you, that's okay also. I am over here off to the side. I'm going to have my x values and my y values just to keep track of where I'm at. So we're starting at an x value of 1 and a y value of 2. And I need to know now, what is y prime at this point? So if I plug in 1 for x and 2 for y, 2 squared is 4. So I'll have 1 minus 4 over 1. Or 1 minus 4, so that's negative 3. So my y prime is negative 3. So to get my new x and y values, I know that I'm taking a step of 0.1, so I'll be at 1.1. And to get my new y value, I've got to use the formula. So we're currently at a y value of 2. And now I'm going to add to that our derivative at the point, so that was negative 3. Times our time step, which was 0.1. So that's 2 minus 0.3, or 1.7. So that's my new y value, is 1.7. Now you'll notice that typically with these problems, the numbers get messy in a hurry. That's why if you're not allowed to use a calculator, which is what's stated at the top of Didel's final review sheet, if you're not going to be given a calculator, I do not anticipate you having to do more than 2 iterations or 2 time steps for this, because the numbers just get really messy. So to get my y prime at that point, I would be looking at 1.1 minus 1.7 squared divided by 1.1. Now this is the point where you should be asking me, do I have to simplify that? Heck no, you don't have to simplify that. We're just going to plug that into the formula. So I know that my new x value will be 1.2, and to get my new y value, I'm going to use the formula. So my new y sub n is at 1.7. That's the point we're standing at. And we're going to have plus that entire derivative. So 1.1 plus 1.7 squared over 1.1 times 0.1. And we are going to walk away and say that y of 1.2 is approximately equal to this. Don't simplify. Oh, someone just said I'm missing a minus sign. Thank you. Thank you. When I copied our value for the derivative over, should have been a minus sign. Thank you for catching that. So first of all, in terms of classifying it, I know it's a differential equation because there's a derivative and an equal sign. It's all I need to be a differential equation. I know it's first order because I just have a first derivative in it. And I also know that it's not linear because y is inside of a cotangent. So automatically, if I've been asked to solve this, I know it has to be separable because we've only got those two choices in 17b. So this is separable. So if it's separable, my first trick is going to be to make this look like dy dx equals something with x's in it times something with y's in it. So I'm going to start by adding that cotangent squared y over and dividing by 1 plus e to the x. Now I know that I didn't exactly make that look like something with x's times something with y's, but I can really quickly separate that out and move that cotangent squared y over here and just leave a 1 on top right there. Now I have it in this form of something with x's times something with y's. One of the places that seem to be tripping people up a little bit is this dy dx, that's made the decision for us which side of the equation the y's have to be on and which side of the equation the x's have to be on in the end. Because my only option is to integrate dy. I can't integrate a 1 over dy, just like I can't integrate a 1 over dx. So right now, I'd be multiplying both sides of the equation by dx, which means I'm going to keep my x's over here, and I'm going to move my y's to the other side. So bringing those over, I'm going to end up with cotangent squared y dy is equal to 1 over 1 plus e to the x dx. And then we can go ahead, oh, I was dividing by cotangent. Thank you for catching me on that. So that should be a 1 over cotangent squared y. And that's what our setup has to be to move forward in the integration. Would anyone like to see me finish off the integrals? They're both tricky, but also probably both reasonable for a DDEL exam. Okay, so on the left-hand side, the trick is that we really need a trig identity. So 1 over cotangent is the same thing as tangent. So rather than having this as 1 over cotangent squared y, I really want to think about this as tangent squared y dy, and then take that one step further. We don't have a nice integral for tangent squared, but we do have a nice integral for secant squared. So we're going to want to use that trig identity that I mentioned before and switch tangent squared y to be secant squared y minus 1. On the right-hand side, we have a different kind of trick that we want to play. So on the right-hand side, sure would be nice if this was a u substitution. But 1 plus e to the x, if I were to set that equal to u, the derivative would be e to the x. So I'm missing an e to the x in the problem. The easiest way to solve that, and really this is just kind of a trick, or rather it's a cleverness that we're going to employ. Because I don't have the e to the x that I need in order to do a u substitution, I'm going to creatively multiply by 1. I mean, I'm going to multiply the top and the bottom by the same thing. And that thing that, so the thing that I'm going to multiply by here is e to the negative x over e to the negative x. I'm going to pause for a second and address the question about, isn't that just ln of something? And the problem is, in order to write this as natural log of something, this would need to be 1 over u du. And it's that du that I don't have right now. So I'm going to have to get creative and make it show up. The reason I'm multiplying by e to the negative x is that now when I distribute that e to the negative x through in the denominator, e to the negative x times 1 is e to the negative x, but e to the x times e to the negative x, that's as if I'm saying, instead of e to the x times e to the negative x, that's like I'm saying e to the x divided by e to the x. So that's going to be equal to 1. Now I'm going to take exactly that idea of natural log, because now I can look at that, and if I set the denominator equal to u, then du is negative e to the negative x dx, which I almost have in my numerator. It's only that minus sign that's throwing me off. So this I can switch around to write in terms of u's as negative the integral of du over u. Now both sides of this are ready for me to take the antiderivative. On the left-hand side, when I take the antiderivative, the function whose derivative is secant squared is tangent. So I end up with tangent of y minus y is equal to, and on this side, you're right, I do end up with an ln. So I've got negative natural log of u, and I'm just going to go ahead and plug in what our u was, that e to the negative x plus 1. So again, when we're talking about classifying, I know that it's first order linear if I can write it as y prime plus something times x equals, sorry, y prime plus something times y equals something. And if I call that p and I call that q, then our general method for solving a first order linear is to find an integrating factor. And the way we find that integrating factor is always the same. I'm going to raise e to the integral of whatever our function is right here. Once we've found that integrating factor, we're going to multiply every term here by that integrating factor. So we'll end up with mu times y prime plus p times mu times y is equal to mu times q. Now the result here should each and every time be a product rule, meaning we can combine this together to say mu times y prime. Next step, I'm going to undo that product rule. And since I had a derivative over here and I sort of undid the derivative, that means over here I'm going to find the antiderivative, or write this as the integral of mu times q dx. Now my last step is going to be, well, okay, second to last step. I'm going to evaluate this integral. And I'm just going to write this as something, right, because I didn't really give us a function. But this integral is going to be something plus a constant. So in my last step, when I solve this to make it say y equals, one thing that we have to remember is that means that it's the something divided by mu. This piece often simplifies, plus c divided by mu. This will not. So if you forget to add the plus c here, you might end up having like everything cancel out in the problem and getting the wrong answer. So when you're doing these first order linear, it's super important to remember to keep that plus c at that step where you're taking the antiderivative. For simplicity, just because I think you're likely to see it as a tank with salt or sugar or something flowing in, we're going to be given some kind of a rate in, and we're going to be given some kind of a rate out. So the change in the amount of stuff, or I'll just call that dA dt for the amount of stuff, it's going to be a rate in minus a rate out. But secretly, each of those rates is usually two pieces. We're going to have one piece that's dealing with the concentration. Right, we're going to have one piece that's dealing with the concentration and one piece that's dealing with sort of how fast it's flowing. So I'm going to have some kind of concentration. Can't quite fit the word concentration, but in both of these, I'm going to have some kind of concentration times some kind of speed element. So for this problem, let's say that I have a tank that holds 400 gallons and I have 20 pounds of something in the tank. So that concentration for what's coming in, we don't know yet. I didn't give us a speed yet, but I already know part of the concentration for what's flowing out. And in terms of what's flowing out, because it's flowing out of the tank, the total amount of stuff for that concentration is always going to be whatever it is we're talking about. At the bottom is going to be some sort of volume. So there more goes into the volume part. Let's say that what's coming in has a concentration of 1 pound per 5 gallons. So that's an amount of stuff divided by a volume. So my concentration here was 1 pound per 5 gallons. That means that my speed piece should be telling me a volume per unit time. I know that's not exactly speed, it's actually flux, but sure, we'll call it flux. We'll give it the fancy physicsy word. But it's that volume per unit time. So if this is flowing in at 2 gallons per minute, then that's my 2 gallons per minute kind of volume. If it's flowing out at the same rate, then the total volume in the tank doesn't change. But if it's flowing out at a different rate, then that means the total volume of stuff in the tank is going to change, which will affect the concentration of what's coming out. So if this is flowing out at 5 gallons per minute, then that means each minute I have a loss of 3 gallons because I've got 2 coming in, but 5 going out. So over here, I'm going to squeeze this over. So over here for my flux piece, or my volume per unit time, that would be the 5 gallons per minute. But for my concentration, we started at 400 gallons, but we are losing, so it's negative, 3 gallons per minute. So I'm going to put that T there. So things to be careful of for tank problems. We want to check, is the gallons per minute in equal to out? Because that's going to determine whether we have to do something to adjust for the volume in the tank. The other thing that we want to watch out for are statements about like pure water. And pure water, the thing we want to remember there is that the concentration is 0. So if I have pure water coming into the tank, then that concentration in would be 0 pounds per 5 gallons, or 0 pounds per however many gallons, because it's pure water. So these are sort of the 2 things to watch out for in tank problems. The whole idea with the SIR model is that we're assuming that we have some population, and in that population, some people fall under the group of being susceptible, meaning they might get infected by something. We have some part of the population that already is infected, and some part of the population that is recovered or removed. Now, we don't like to think about the grim reality of this, but if it's a disease that you couldn't recover from, then we say removed because that individual has died. So R can either stand for recovered or removed, depending on what particular model you're looking at. So the reason that we put this kind of under the category of a tank model or a tank problem or a compartment problem is that there's a clear direction of flow. You're susceptible to the disease, and some percentage of the population that was susceptible will be infected. And then some percentage of the population that is infected will, in fact, recover. So we model this with a differential equation by saying that the rate of change for the number of people that are susceptible to the disease, and just like with a tank problem or a compartment problem, we're thinking about this as a rate in minus a rate out. So when we think about the number of people in the population that are susceptible, if we assume that the total number of people in the population is not changing, then we can't ever get new people in. We won't get more new susceptibles. In terms of that rate out, well, now we want to think about what's happening. Our population that is susceptible, the reason it's moving out of susceptible is because it's moving in to the infected population. So there are different models. This particular model that was discussed in class the other day assumes that that rate of infection is proportional to, meaning it's equal to a constant times, and I'm going to use B because that's the constant that our textbook uses, is equal to a constant times, and then that rate of infection, it's proportional to sort of the interaction rate between our susceptibles and our infecteds. Meaning, if I have lots more people who are, if I have a large population that's infected, then I have fewer susceptible because more of my overall population is here, not here. But in general, that transmission is going to happen because my susceptibles are interacting with the infecteds. So the rate is proportional to both the number of susceptibles and the number of infected. Now let's look at the number of infected individuals. Well, for that rate in, the people that are moving into that infected phase are the ones that are coming out of our susceptible phase, which means that rate in is BSI. Now, in terms of the rate out, here we want to think about a certain percentage of the individuals who are infected will recover. It doesn't matter if you've been infected, it doesn't matter in terms of like moving out of the infected phase. We can't move out. The underlying assumption here is that we can't move out of the infected phase and back into being susceptible. We can only move out of the infected phase and into the recovered, which means this, we need another constant. The one our textbook chooses is mu. And then that last part is our dr dt. And what's coming in to our group that is recovered or removed is this group right here, meaning that's going to equal mu times I. There is no rate out for my recovered individuals. We're assuming that once you're here, you stay there. You don't ever become susceptible again. And because you've recovered, we assume there's some level of immunity and you're not going back into the pool of infected individuals. Product, length of a vector, angle of a vector, and vector projection. So let's look at some of the formulas there that show up in 8.3. in the context of 8.3, when we were talking about vectors, we were writing them as row vectors. But then once we started talking about matrices, we often write vectors as column vectors. So just be prepared for vectors to show up in either of those forms. If I give you a vector A and I wrote it as a column vector, then I might say like 1, 2, -3. I could also write that as a row vector, in which case I would put commas between the numbers, or we also had notation for the standard basis vectors to write this as 1i plus 2j minus 3k. And all of these represent the same vector. It's just 3 different types of notation for the same thing. If I went to find the length of this vector or the magnitude of the vector A, I'm going to find the magnitude of the vector A or the length by taking the square root of each of the components squared. So 1 squared plus 2 squared plus -3 squared. What's that? 1 plus 4, so I'm at 5 plus 9, so square root of 14. So that's the length of this vector or the magnitude. After we talked a little bit about vectors, then we got on to things like dot product, which allows us to do vector projections and find angles between vectors. So let me introduce another vector. Let's call it B. And my B vector, I am going to choose to write as a column vector. And so my B vector, maybe that's 1, 0, 2. So if I went to find the magnitude or the length of B, I'd have the square root of 1 squared plus 0 squared plus 2 squared, or the square root of 5, not 15, square root of 5. With those 2 vectors, I can now talk about things like the dot product. So if I take the dot product of A and B, or A dotted with B, that means that I'm multiplying each of the components together and adding between components. So that's going to look like 1 times 1 plus 2 times 0 plus -3 times 2. That's 1 plus 0 minus 6, so I get -5. Now there's another form for the dot product that involves cosine of the angle between the 2 vectors. So A dotted with B, we can also write as the magnitude of A times the magnitude of B times cosine of the angle between them. In general, I don't know the angle between the 2 vectors. I'm just given vectors in component form. So finding the dot product this way is usually the easier method. But that means that I can exploit the fact that I know that this is -5. And I know what the magnitude of A is, and I know what the magnitude of B is. So that I can rearrange that equation and find the angle between the 2 vectors. So in general, I'm getting that angle between the 2 vectors by looking at cosine inverse of A dotted with B divided by the magnitude of A times the magnitude of B. And because you are not supposed to be using a calculator on the final, we would not simplify this most of the time. There is an exception to that, and that exception comes into play if I take the dot product and I get an answer of 0, then I automatically know that the angle between the 2 vectors is 90 degrees, or they're perpendicular, or I can also say they're orthogonal, or I can say they're normal to each other. So if this dot product is 0, that means we had to be looking at cosine of 90 degrees in order to get a 0 on this side of the equation. formulas that you're going to want to know when it comes to vector projections. So we write a projection of A onto B is equal to the dot product of A dotted with B divided by the magnitude of B times B over the magnitude of B. Now, this portion right here is referred to as the scalar component or the scalar projection. So sometimes this is written as the comp of A onto B, and it's a scalar. This portion right here is a unit vector in the direction of B. So if you're asked for a unit vector, you will take the vector and divide each element of that vector or each component of the vector by the magnitude or the length of the vector. So that's our scalar component, and that's a unit vector in the direction of B. And together, that forms my projection of A onto B. Moving on to section 8.5. Can we do an example for this one, for a vector projection? Sure. So I don't remember what my A and B were from the previous problem, so I'm just going to make up a new A and B. If A is equal to, and this time just for fun, I'll write it as a row vector. So let's say A is 1, -1, 0, and B is 2, 0, 3. Then if I look for the projection of A onto B, then I'll take the dot product of these two vectors. So our dot product would be 1 times 2 plus -1 times 0 plus 0 times 3. So there's my dot product of A dotted with B. And we're going to divide that by the length of B, or the square root of 2 squared plus 0 squared plus 3 squared. And now I'm going to multiply that by my B vector divided by its length. So if I clean up the length here, that's 9 plus 4, so square root of 13. So I'm going to multiply this by the vector 2 over square root of 13, 0, and 3 over the square root of 13. Now, I'm guessing someone's about to ask me if you need to simplify. Theme of the day, please don't. Spend that time thinking through another part of the exam. Spend your time thinking about the math. Don't spend your time trying to clean up the arithmetic. So really, the vector projection, it is a formula. You need to be able to use the formula to plug things in. So there is my system of difference equations. And I picked up the red marker that's dead, so let me get rid of that one. So one of the things we might need to do with this system of difference equations is to draw this out as a diagram. So here I've got x's, y's, and z's. And if I look at the x's, I'm getting x's from my existing x, so that's going to look like a loop, from x back into x, and that's at a rate of 0.9. And we're also getting x's from y. So we're getting x's from y at a rate of 0.4. If I look at my y's, some of my x is returning back to y at a rate of 0.06. And I've also got y cycling back on itself at a rate of 0.1. So it doesn't really matter where you draw it. Here I'm going to draw this one at the bottom just for space. So that's going to be a 0.1. And then if I look at my z's, I'm getting part of my z from x. So from x, I've got a path into z here at a 0.04 rate. And I'm also getting some z from y at a 0.5 rate. And z is cycling back on itself. And because there is no coefficient here, that means there's an invisible 1. Now I need to set this up as a matrix. So as a matrix equation, I'm going to write my x sub t plus 1, y sub t plus 1, z sub t plus 1 vector is equal to, and now I need a matrix, times x sub t, y sub t, z sub t. Now I'm going to write something in that I usually write, and I'm only writing this for myself. So I know that these rows are my x, y's, and z's, and I know that first column is what's coming from x, my second column is what's coming from y, my third column is what's coming from z. And I just write those as cues to myself. After I've filled in my matrix, I'm going to erase my self notes there. So in my top row, I need to know what's going into x from x. So I've got 0.9 from x back into x. I need to know what's coming from y and going into x. So from y into x, I've got 0.4. And here I need what's coming from z and into x. And there are no arrows that are going from z into x. Now notice, I can also get this directly from our difference equations, because this just represents the coefficients of my x sub t, y sub t, and the invisible z sub t term. If I put in an invisible z sub t term here as well, then this matrix should correspond to each of the coefficients if everything is lined up correctly here with all the x's together, y's together, and z's together. So they should all match. So now my second row is telling me what's happening with y. So I need to know what's coming from x into y. So from x into y is 0.06, which again matches up with my coefficient right here. Now I need to know what's coming from y into y. So y into y, I've got 0.1, and z into y is nothing. So again, that matches my coefficients up there in the difference equation. Our last line here, what's coming in from x into z, x to z, here we go, x to z, 0.04. 0.04. From y into z, I've got 0.5. And z into z, I had a 1. Now that I'm done setting up my matrix, I'm going to get rid of these. These were just telling me, reminding me what goes where. Really, I think there are a couple of things that you need to know in terms of formulas. So for the inverse of a matrix, we have a formula for a 2 by 2. So if it's a 2 by 2 matrix, and I write our A matrix as A, B, C, D, then the determinant of A is minus, so A, D minus B, C. If my matrix is a 3 by 3, okay, I don't want to write A, B, C, D, E. It's just, we're not going to write that. I am actually just going to put a matrix here. So let's go 2. I said 2. I wrote a 1. That's kind of funny. Let's make that a 2 and a 0, and 0, 3, -1, and 1, 0, 4. Our textbook gives us one method for finding the determinant of a 3x3 matrix, but I noticed that Dedell also posted a handout on cofactor expansion, and that's the way that I prefer to find the determinant of a 3x3 matrix, because that's the way that we would end up using in linear algebra, which is, I think, why Dr. Dedell posted that alternative method for the determinant of a 3x3. The reason that the cofactor expansion method is nice is that if I happen to give you a matrix and put a bunch of zeros in it, the cofactor expansion ends up being the much faster way to find the determinant. So I'm going to find this determinant two ways. So I'm going to start by doing it the textbook way, and then we'll do the cofactor expansion way. So for the textbook version, I'm going to take the first two columns of the matrix and replicate them over here. 1, 0, 1, 2, 3, 0. Next, I'm going to use a similar method to up here, minus. So first we're going to do all of our positive. So my positive are coming as I move diagonally from the upper left corner to the bottom right corner. So I'm first going to go through 1, 3, and 4. So that's going to give me 1 times 3 times 4, so that's 12. Then I'm going to go 2 times negative 1 times 1, which is going to give me negative 2. Then I'm going to have 0 times 0 times 0. Okay, that wasn't very exciting, but we'll write it anyway, plus 0. Then we're going to come through and go the other direction, and these we're going to make negative. So I'm going to go 0 times 3 times 1 and get 0, but just for completeness, I'm going to write this as negative 0. Then I'm going to have 1 times negative 1 times 0. Okay, I made a lot of zeros in here, sorry. So that's also going to be a negative 0. Oh, I made a lot of zeros. 2 times 0 times 4. So that's again minus a 0. So overall, I think I'm going to get 10. So the determinant of this matrix is equal to 10. And I would say this is a really straightforward way to find the determinant of a matrix. It's a common one that you see. It's the way that it's usually taught in our 21 series textbook as well. It's a formula for how to do it. That cofactor expansion piece that Dedell posted some notes on, would anyone like to see me do it with cofactor expansion? Okay, got a couple yeses, so I will go through the cofactor expansion version of this. And maybe I will, maybe I'll just write a whole nother matrix for us, because I don't know that I can erase that and make it pretty. And just taking a look at the time, I don't think that I'm necessarily going to get to eigenvectors and eigenvalues. I think I'm probably going to end here on determinants and inverses. So if anybody is holding out for eigenvalues and eigenvectors today, I just don't think I'll have time. But luckily, that's what we were working on all this week. So hopefully you're feeling okay about that stuff. So here's my 3x3 matrix. Let's go 2, negative 1, 4, 0, 5, 1, 1, 2, 2. Whenever we're going to, oh, there's a question. Yes, I will be doing another review session on Monday. On Monday, I'm really going to focus on working problems, not just covering sections the way that I was doing today. So if you have particular questions that you'd like me to see me go over on Monday, I'm happy to do that. You can either get those to me ahead of time or ask me in the chat on Monday. I will come prepared with a bunch of practice problems also. So if nobody has particular questions, you can just pick sections and I will do problems from there. Oh, and someone's asking about the time on Monday. So let me quickly check. I think I said 10 to 12. Does that sound right to other people? 10 to 12 is what I put on my calendar. So yeah, 10 to 12 on Monday. Okay, so for the cofactor expansion, the first thing that we want to identify in the problem is where we have the most zeros. And it doesn't matter if it's a column or a row that has a bunch of zeros, we definitely want to choose something, either a column or a row with zeros in it. Now I only give us 1 0 this time so that I can better illustrate what happens in the cofactor expansion. So we can choose to either expand this across column 1, or we can expand this across row 2. And so, yeah, someone was asking on Monday, can we start by going through sections 8.7 and 8.8, the eigenvalue, eigenvector stuff? For sure. We can start with that on Monday. So here is, I'm going to choose to expand across column 1. So when we do the cofactor expansion, I'm going to take those values, the 2, the 0, and 1, and I'm just going to write them down. So I'm going to have 2, 0, and 1. And you'll see in a second why having extra zeros is super nice. The next thing that I'm going to do is to figure out the signs. So if I imagine this 3 by 3 matrix as a checkerboard where I'm alternating between positive, negative, then that 2 would be, if I think about this as a checkerboard, this would look like positive, negative, positive, and then the next row would be the opposite, negative, positive, negative, and then the final row would be positive, negative, positive. The other way to think about this is that I can get the sign for the position I'm in by doing -1 to the row plus column. So this 2 was sitting in this spot, which means I know it's positive, or I can think about this as 2 times -1 to row 1 plus column 1, so the rows plus columns. And there's a linear algebra reason for that we don't need to worry about right now. This is 0, because it's sitting right here, I know that's in a minus spot, but I can also figure that out by looking at -1 to this is in the second row, first column, so to the 2 plus 1. So that's going to be a -0, and this one's going to be a +2. And then that 1, I know it's sitting in the spot with a plus, or I can think about it as -1 to, this is row 3, column 1. So that'll be a +1. Now the next piece is what we're multiplying each of these numbers by. So when I look at the 2, to figure out what I should multiply the 2 by, I'm going to imagine getting rid of the column that the 2 is in and also the row that the 2 is in. So if I eliminate this row and this column, then I'd be left with a 2 by 2 matrix. And we know how to take the determinant of the 2 by 2 matrix. I'm going to get 5 times 2 minus 1 times 2. So that 2 gets multiplied by 5 times 2 minus 1 times 2. Now you can see already that if I had a 0 here as well, we'd be done. Because I don't actually need to compute this next piece. It's going to be 0 times something. So if that weren't a 1 and that were actually a 0, then this would also be a 0. And I'm done. My determinant of this matrix is 2 times 10 minus 2, or 8. So I'm already done. The determinant of that matrix is 16. So if he happens to give you a matrix on the test where there are 2 zeros, either in a row or a column, then this cofactor expansion is super nice. But let's go back to the original problem I wrote, where that's a 1, which means this is also a 1. So I've got a 1 there, and a 1 there, and a 1 there. So similarly to what we did with the 2, I am going to, that 1, it's in the 3rd row. So I'm going to imagine that I've blanked out the 3rd row and the 1st column. So if I do that, I'm left with a 2 by 2 matrix where the determinant is -1 times 1 minus 4 times 5. -1 times 1 minus 4 times 5. So -1 minus 20, so it's -21. So overall, the determinant of that matrix is -5.